So this lecture focuses in on collision theory. So far this semester, what we've been talking about are sort of the mathematical representations of kinetics, and so we've been talking about things like integrated rate laws, which relate concentration to time, or rate laws that relate concentration to rate. And we've been doing this from like a purely mathematical perspective. And what we're going to do today is we're going to try to link it more to what's actually occurring physically. And we're going to make some arguments based off of some simple ideas that we sort of encapsulate in this idea called collision theory. We're going to make some arguments about how reactions occur, what has to happen from the standpoint of molecules and particles involved for a reaction to occur, and then how we can link it to those important objects that I just mentioned, rate laws and integrated rate laws. All right, and so before we get to that mathematical linking, let's just start with discussing collision theory in general, what it means, and how we're going to use it to describe how a reaction occurs. All right, so the ideas behind collision theory are pretty simple. Collision theory dictates that for a reaction to progress, particles must collide with the correct orientation and sufficient energy. All right. For a reaction to progress, things have to hit each other. They not only have to hit each other in the correct spots, but they have to hit each other hard enough to actually get a reaction to occur. All right. Pretty simple idea, but it sort of builds the whole physical basis for how we think about reactions occurring. As a quick little example, let's take a look at an acid-base reaction, and these sorts of reactions become more and more important to us as we go through the semester. And you're sort of familiar with acid-base reactions from your last semester course. So let's take HCl, which is an acid, and let's interact it or react it with OH minus. What we'll get out of this is it looks like a neutralization. What we're going to get is water and then Cl minus out as products. So here's a reaction, and we can monitor the reaction rates involved. We could get a rate law, we could get an integrated rate law, but what's actually happening to make the reactants go to products? Well, things are hitting each other. They're hitting each other in a particular way, and they're hitting each other with enough energy to break bonds. Okay, so let's take a look at some Lewis structures here. So HCl is a pretty simple Lewis structure, and the Lewis structure is the geometry. We just have this linear structure that we're analyzing. OH minus is also a linear structure, and I'm just going to draw it down here, and then we're going to talk about the different things that it could do. All right, so here's OH minus and its Lewis structure. Now what we get out at the end is something happens with these two molecules, and what we're left with is now, all right, a water where the O that's involved in this reaction is now attached to two H's, all right, and we also get a Cl minus. All right. So the Cl is no longer attached to anything, it's just kind of floating away by itself. So what has to happen for this to occur? Again, it's a pretty simple idea, but it's also, like I said, the fundamental thing that we'll use to describe reactions. So here's OH minus. We know that to get the O attached to two H's, if I take this O, and these guys are in the same solution, and the O that's part of this hydroxide hits the Cl part of HCl, right? That's not going to lead to a successful transition of reactants to products, all right? That's a collision, and it might be a hard collision, it might have a lot of energy, but it's a collision that's not going to give us what we want in terms of a product, right? It's an unsuccessful collision, okay? So this is actually not useful. It'll happen in solution, but it won't get us to products, all right? We could also have a situation, and I'm just gonna use like a like curvy arrow, and all this is saying is like, just imagine it like slowly meandering up to this H. We could also have it hit in the correct spot, but maybe it's going really slow. These guys are coming close to each other. they're not moving that much in the sample, and so what we get is we get a collision, but it's a really light collision. In that case, there's not enough energy to really rip this H away and attach it to the O, and that's what we need for the reaction to progress, all right? So not only does orientation matter, so this looks like it could possibly be successful, but again, it's not hitting with enough energy. Not only is orientation important, but also energy, right? So if we take a look at hitting OH minus with a lot of energy, and I'm just gonna use this black arrow to say, all right, we're hitting the correct spot. We have enough energy to rip this H away, all right? This is the only instance where we can actually progress and get water and then free up Cl minus to float away by itself. So one more time with collision theory, things have to hit with the correct orientation. That means they have to smack together in the correct spot, and they also have to have sufficient energy, all right? So then what do we do to actually sort of mathematically model this? So this is an interesting idea. We also have to kind of think about experimental controls, because we mentioned some things here, a slow motion versus a fast motion. We have to think about what experimental controls we have to enact those sorts of processes, all right? And that leads to a discussion where we now focus on K. So we go back and we focus in on the rate constant. And all our modeling with collision theory has to deal with incorporating these ideas, correct orientation, correct energy, all right, into K itself, into the rate constant. So if we focus on K, there's a lot of sophisticated modeling that occurs, that happens in the background. It's interesting, we get to a little bit of it in physical chemistry eventually, but just kind of realize that there is a lot of important things happening in the background, but for the purposes of this course, we just kind of have to have an understanding of why K is the focus and what information is there, right, from the level that we actually describe next. So if you think about where you saw K and how it sort of influences what we're talking about from a kinetic standpoint, it's one of the main components of a rate law. And if you look at this, right, we see that K is actually proportional to rate. And that's the important thing to kind of realize here. As K gets big, what happens to rate? It also gets big, all right, because they're sort of multiplicative, and on the opposite side, it's a proportionality constant. Excuse me. As K gets small, what happens to rate? It also gets small. They're directly proportional. Okay, so then how does this work with actually thinking about collisions? Well, what we're going to do is we're going to model, all right, these ideas from collision theory into K. So let's think about these ideas. What we have to really have with K, right, is a way to put in motion and a way to put in orientation, okay? So here are our ideas. And the first idea with how we're doing this modeling is that K actually depends on temperature. So when I write something like this, all right, this is saying that K is a constant that's sure and right and good, but it's only a constant for a fixed temperature. And in fact, the reason that we know that K should be temperature dependent is we just got done explaining how the more collisions you have that are successful with the correct energy, all right, the more products you'll make. What that means is that K is tied to temperature, all right, because motion is tied to successful collisions, okay? So again, if K is dependent on temperature, and I can make a modeling occur where K increases as temperature increases, as K goes up, rate goes up. As rate goes up, you're making more products, and that's the connection you need to make. A higher K, because of more collisions, because of a higher temperature, means that you're gonna have more products that are made, and then that means you have a higher rate, okay? A real important idea, pause it, rewind a few seconds if you have to hear it again, okay? So K depends on temperature, all right? The more motion that we have, and remember, temperature is a measure of the average kinetic energy, so more motion means that we have an increased temperature, all right? The more motion that we have, the more collisions Just because we have a collision doesn't mean it's successful, but the more collisions we have, the more successful collisions we have. And the more successful collisions that we have, the higher the rate, right? The higher the rate. Right. K also must have some sort of influence in terms of particle size, or particle size must influence K in some way. And so the reason behind that sort of thought process goes like this. If orientation matters, then if you have a bigger surface to hit, right? If the molecule's simply bigger, all right, then it'll be easier to have successful collisions. And so inside K, there must also be sort of a measure for how big a particle is. So still underneath our like modeling notes, all right? K must also consider particle size. And when I say K must consider, I'm really referring to like the modeling of K. So K must also consider particle size, all right? Because we have a bigger particle, all right, it's going to be easier to get a successful collision. And if it's easier to get a successful collision, then think about what has to happen. If it's easier to get a successful collision at a fixed temperature, then what you're going to have is an increase in rate. And again, rate is proportional to K, so you would have an increase in K. So not only do we have to have energy considerations inside K, but we also have to have collision information inside K as well in terms of size, right? And just another real quick example on this. Let's say I was looking at like 2I minus forming I2 versus 2, or let's just do 2 I's, right? So atomic I's, right? 2 H's forming H2, right? Atomic H's, so no charge, no ions there. Remember what we know about I based off our periodic trends. I is really, really big. So here's an I and here's an I, right? And they're moving around in a sample, and oh, I is really big. It's real easy for these guys to hit each other with enough energy. Just because they're so big, there's going to be more smacking into each other, which means there's going to be more product made, which means that the rate for that temperature is going to be higher, right? If you look at H's in comparison, I'm going to draw them really small, and hopefully you can even see them, but you kind of get the idea. If you look at H's in comparison to I, they're very small. So in a sample, it's more likely for these H's to just kind of zoom by each other. So they won't collide as much just because they're not as big. It's harder for these I's to zoom by each other. If I try to draw these arrows where the I's are missing each other, there's just more area to hit, so there's more collisions. All right. So these ideas then are incorporated into K. There must be a size component, and there must be a movement component or a temperature component. And what that leads to, right, is what's known as the Arrhenius equation. Right, the Arrhenius equation. And the Arrhenius equation does just that. It takes all this modeling information that we have, it takes our ideas with collision theory, and it puts it all into K. What the Arrhenius equation says is that K equals A e to the minus e sub a over r, and I'm going to write it as 1 over t. And so what we see again is a situation where we have an exponential relationship. All right, an exponential relationship. Let's define some variables. All right, so you're familiar with what this looks like. It's a negative exponential. It looks like a decay. All right, A is what's known as the Arrhenius parameter. And for us, right, in this level of chemistry, this contains like your size and your orientation information, okay? Let's just put it this way. This contains size information. So we expect bigger molecules to have a bigger A. All right, bigger molecules should have a bigger A. And a bigger A, what do we see again? You see a proportionality, a bigger A would be a bigger K. All right. Here this is 1 over T, but T is temperature in Kelvin. This is our good friend R. It's the R that we've seen before. But there's 2 versions of R. Guess what we're going to use here? We're going to use the energy version of R that has joules in it. And this E sub A right here, all right, this is what's known as the activation energy. All right, the activation energy. So a real quick review of what we went over. All right, collision theory is how we view reactions occurring. Things have to hit with the correct orientation and the correct energy. We can think about modeling that process through K. All right, we can think about taking K and breaking it down in this Arrhenius fashion. And we can build in size information, where if we have bigger size, we have a bigger K. And we can build in temperature or motion information into our modeling as well. Oh, there's a 1 over T here. This looks a lot like our vapor pressure analysis we did earlier, and that's a connection I'm going to make over and over again. But what does this 1 over T mean? This means that when T is big, right, when T is big, 1 over T is small. When T is big, 1 over T is small, and so your exponential is small. And if your exponential is small, your K is big. So I'll end with saying I just made some important connections. Stop, rewind, again, write it down, all right, make sure you get it. But this ends this video. The next video, what we're gonna tackle is sort of thinking about this activation energy, what it means, how it relates to our modeling discussion we just had, and then also applying mathematics to these ideas that we just went over.